Hello, my name is Kazuma Nagashima. In this talk, we will present a simulation study which is rapid motor learning. This presentation consists of 6 parts. I'd like to begin with showing our introduction about motor learning. Humans acquire patterns of motor skills improving the prediction of various environmental changes. They are able to take quick and accurate action. The acquisition of such motor skills has been researched in the field of cognitive model architectures. For example, Actual has the vision module and the motor module for interaction with the external world. Actual receives information about the external world from the vision module. Thinks something based on this information, and the result performs motor actions to the external world. The vision and motor modules of the actor have been used for a variety of motor tasks. However, they are inadequate to reproduce human behavior in tasks which require immediate response. One of the reasons Actual does not have a direct connection between the vision module and the motor module comparing CMC, which is a standard architecture assumption. In Actual, visual information has a long path to be transmitted to the motor module. Thus, it takes time to learn motor skills. Next, related works. There is an actual model of skill acquisition called KRK based on fish theory, which is multi-level learning. The study focused on skill retention and defined 3 stages as multiple learning. In the first stage, the task relied primarily on declarative memory. In the second stage, both declarative and procedural memory are utilized. In the third stage, the task depends only on procedural memory. The study models the theory using knowledge compilation of actual function. Based on the study, there are studies for learning motor skills in complex perceptual motor tasks. The study explains internal human processes during a video game environment using motor learning module of Actual. These studies are about learning keystroke timing. The model represents human performance at a high level. However, these studies did not reveal a mechanism to represent rapid human learning. There is also a theory that explains the learning of motor skills. The theory assumes motor schema. Motor schema is knowledge that contains parameters, past motor contents, and past motor outcomes. The knowledge are acquired through perceptual motor tasks. It is said that humans can execute not experienced actions by constructed motor schemas. Thus, we thought that using the theory can explain rapid human learning. We focus on express the cognitive mechanism behind rapid learning. To model the mechanism, this study uses motor scheme theory. Before introducing our model, I'd like to present a simple perceptual and motor tasks. To examine learning rate of human, we set up the following task. In this task, participants manipulate the circular object and trace lines. The lines are displayed in vertical scrolling. In addition, There are three key operations: left, right, and stop, which is this task based on our previous work. We use a crowdsourcing service to recruit participants. The participants engage in the task for a duration of 30 minutes. The indicator is offline ratio, which is that they can't follow the line. It is a high value indicates bad performance on the task, while a low value indicates good performance. From result, we confirmed rapid learning in the early stage of the task. The participants learned the task until around 3 minutes. After that, their learning speed slowed down, and its performance seemed to be converging. I'll present a model. The concept of our study to model rapid learning in the early stage of the task. We used our previous model and integrate motor schema theory into the model. This diagram is the task loop. Firstly, the model checks the external environment and updates the current state of the goal module. Next, the model requests chunks related to active objects in declarative modules. Finally, the model manipulates the key required for the task in the module. This loop is implemented through the vision module, confirming the external world and the motor module's learning. The model sees the external world by vision module. The module recognizing line length and color. These line length and color are used to determine model manipulation. Using this information, actor learns to operate the manipulation. In this study, we use the motor learning module of actor. The value range and number of steps can be set for this module. The module determines the value according to the number of steps from the value range based on the annealing algorithm. The module is used to represent motor control proficiency. In this module, the model learns the timing of key presses. For example, in the beginning of the task, the model may cross the line or not reach the line. Using this module, the model becomes proficient at the task by giving on positive rewards for good behavior and negative rewards for bad behavior. In other words, it is assumed that the model gradually proficient in the task. To facilitate more learning, this study uses the motor schema theory. The motor schema for this model consists of two steps. During the construction phase, the model learns the optimal timing of keystrokes as correction values. The values represent theta adjusted motor learning module. Each theta is used to determine the operation of the model in the table. To search the optimal theta, the steps are followed. Set value range for each parameter. Run a longer simulation than the human experience. This simulation time is 3 hours. Search for rounds that had an offline ratio of 0. Calculate the difference between the maximum and minimum value for each theta and add them together. Sum up the difference of each theta to the total value. select the round with the lowest total value of the theta. This study gets the optimal ranges about theta by the procedure. During the application phase, firstly, we set the range of each theta to an extended optimal range. Next, we limit the possible value of theta to 3 steps. This operation is especially important. By having 3 steps in the value range containing the optimal value, it is easier for the motor learning module to find the optimal theta. In other words, we assume that this manipulation could replicate rapid human learning. Finally, we run a simulation for 30 minutes. Thus, our model reuse of built schema. Now, I present the simulation. To confirm the rapid learning, we run simulations under the same condition as for participants. The indicator is offline ratio, which is the performance. To confirm the performance of the base perceptual motor process in Act R, this study examines settings which are default and twice speed reactions. Note that GAT parameter defines the firing time of productions in Act R. This slide is results of schema construction phase. Figures show the offline ratio for 3 hours each DAT. The blue and green series represent the model and the human result. The blue lines did not reach the human performance. However, during task progresses, the offline ratio became lower and the performance improved. Next, we explored optimal range in the last hour. The candidate rounds have an offline ratio of 0. The candidate round with the lowest differences between the maximum and minimum value of the range is the optimal range. This slide is results of schema application phase. The setting is extending the range from the center of each theta. For example, theta 1 under the setting, the figure shows the minimum, center, and maximum values. Next, figures show the offline each DAT. Each series indicates a different setting which extends the range from center of optimal range. We confirm rapid learning in the task area. To discuss parameters in detail, we calculate correlation and RMSE between the human result and the model results. The base is the result of the first 30 minutes of the schema construction phase. The others are series in schema application phase. We found the best parameter between human and model. Now I summarize the talk. We represent human rapid motor learning using Act R based on motor schema. We confirm rapid learning in the early stage of the task. In the future work, our model performance needs to reach human performance. For example, we find the better optimal parameter. Also, we improve the task loop.